record. Of course, stop me at any time if there's questions. So I'm going to pull this up just to recap where we are at right now. So this is ELT 126. Hopefully that's why you're all here. And we're on week 3. So week 3 is kind of when all of the new concepts come into play. So this week 3 is about capacitive circuits. And so we kind of were introduced to this last week when we talked about what a capacitor is. So it's a little bit more on that. Next week is week 4, and that talks about inductive circuits and inductive reactions. So this week and next week really go together. You'll see that the equations we use, the concepts are very similar. It's almost like comparing, like when we compared, if you remember I think in 120, we have 1 week where we talked about parallel circuits and calculating resistance. And then another week when we talked about series circuits and talked about calculating resistance and how they were kind of similar but different. Kind of how week 3 and week 4 of 120 work. And again, since this is a 7-week course, it goes so quickly because really after that, week 5 is a little bit challenging. But then it's pretty straightforward. Week 6 and week 7 are pretty easy. It just talks about single phase and 3-phase, which are really important concepts for 150, which some of you are in, and 274, a couple of the upper level classes. And then it's week 7. So also there's only 5 weeks for math, which is nice. So you guys are slowly almost complete with the math. And then don't forget about the amateur modules. So this week, and actually we have time, so we might as well touch on the amateur module a little bit. So this week, the module is alternator synchronization methods. So if you haven't started that one, I'm going to launch it and just kind of briefly touch on this. So an alternator, the way I remember it is it's essentially just a generator. It's almost a type of generator is the best way to think about it. It's just a way of converting one form of energy to another. So of course, alternators are used a lot sometimes to kind of supplement power. So you'll see that in this amateur module, they talk about 3 different methods of synchronization of alternators. So what that means essentially is, and I think it gives a pretty good example or definition for why we do this. So let me, right here, objective 2, I'm going to pause here. So this one's only 25 slides too, so it's pretty short. So we might as well start at the beginning. But essentially the reason that you would have to do this or connect or synchronize the 2 alternators if you ever have to have 2 in one application. And the reason you would have 2 alternators in one application, and when I mean one application, I mean like one machine or one piece of equipment. Sometimes you have 2, and the reason for that is if you have a lot of power demand, and so you need more energy essentially, because again, alternators are a way to kind of they convert mechanical to electrical energy that we can use. So sometimes you have to have 2 if you don't have enough energy. And by having 2 and by connecting them in parallel, what it does is it essentially gives you more current, but you have the same voltage, which is important because obviously for equipment, we need a certain amount of voltage, but the current capacity needs to be greater because we need to have more power again. And that goes back to kind of Ohm's law and the relationship between power and resistance and voltage and current. So kind of works similar to how in parallel, how batteries work if they're connected in parallel. So if you remember, the voltage always remains the same in parallel, if you remember that, and that's because each pathway needs the same amount of voltage, but they have different currents, right? Because sometimes they need to go faster depending on what pathway they're at. Same thing here. So same voltage when you have 2 alternators, it's just sometimes it allows you to get more current, which is sometimes what you need. And just a reminder for these L1, L2, and L3, because these are depicted a lot. You'll see where it says L1, L2, L3. Essentially, I think of those as the different lines, like the hot wires. And we'll actually talk about this today in 150 as well, because they use that notation in electrical blueprints as well. So you can see here that, and this is just like a diagram configuration, where you can see the alternator 1, alternator 2, and they're connected in parallel. So you can see that there's pathways that are connecting both of them. So definitely kind of skim through this. I don't want to skim through all of it and waste too much of your time, but essentially you need to synchronize the two alternators just to ensure that they're working together and they have the same parameters, so the same voltage, the same frequency, the same polarity. If they don't match or if they don't have the same voltage or any of those parameters, it can be pretty dangerous. So you can see here that's what this warning is telling you. So this is definitely really important. And basically what this amateur module does is there's 3 ways to kind of synchronize these two alternators. You can see they're called the 3 dark synchronization method, 2 bright, 1 dark, and then the synchroscope method. I had to look how to spell that. The 3 dark is the one that's the most common, and that's the one that I would focus on as you're reading this. So I'm not going to go too far into it, but you can see here that this is, again, showing the configuration of all of them. Essentially, 3 dark just means they're utilizing lamps. So they, like, if you, maybe I'll search it for a picture if we have time in a minute here, but like essentially there's like 3 lights in the 3 dark method. And the idea is once these 2 alternators are synchronized, the 3 lights are going to beat at the same drum. Essentially, they're going to be getting dark and getting bright at the same intensity at the same time, and that's going to indicate that both alternators are synchronized. So definitely take a look at this, and as you're going through this at the end, it's going to pull up a little simulation. So this skill 2, so whenever you go through the amateur modules, I don't know if you've noticed, but they all have this skill. And if you, so I clicked on skill 1 here. Hopefully it loads, if not. So the skill here is if you click on, sometimes you have to click on the equipment and it'll pull up this manual. So essentially this is what you would do if this class was in person. So if this ELT 126 was ever in person, you would probably have one or, a couple labs throughout the semester, and we would do this lab. So essentially, this is kind of what you'd be given at the beginning of the lab period. You'd read through it, and then you do the hands-on skills in it. So I just wanted to touch on this since this isn't a very hands-on class because it's online. It's still important to kind of read through this and make sure that you're following it. So you can see here that for this one, it's showing the connections that you should have. So to kind of read about it here, talks about the generator is on the left here, and then the synchronous motor, which is the alternator, is on the right. And then it wants you to wire it a certain way. So it kind of shows you here how you would wire it. So this is what you would do again in the lab. You would wire this as it shows. So you can see that all of these lines are showing how you would wire it. So if you zoom in, which will let me zoom in because actually, yeah, it's kind of interesting to note all of, you can see L1, L2, L3. And then so I just wanted to point out a couple things. I'm not going to go through this completely just because I'd rather you go through it, and then if you have questions, ask me. But a couple of things I wanted to point out, like as you're reading these skill manuals. So the first one is when you look at the pictures here, like the figures, it'll reference that a lot of times in like the step-by-step instructions. So it says, like, for example, set up the electric machine learning system, which is essentially like, I don't know if you've ever been into the STEAM lab on campus, but the electric machine learning system, basically Amatrol itself is like, they sell a lot of these electrical toolkits, and they're kind of like mock simulations for how things might look in a machine shop or a factory. And that's what the STEAM lab we have on campus is. I don't know exactly if we have this one, but you can see that it'll say like how to set everything up, or a lot of times in this manual it references figure 1, 2, which is again this figure. So it says like to connect the motor, I showed in figure 1, 2, and to connect the switch and the lamps and the alternator as shown in 1-2. So this is kind of like the main reference you would use if you were doing the skill in person. And it is nice that a lot of times they'll give you both a pictorial diagram and a schematic diagram. The difference is a pictorial diagram is just the picture, then it's kind of a general overview. A schematic is more detailed. So you can see that the schematic itself is a little bit more detailed. It's giving you the exact wires when setups, and then it shows you this here is a switch. This is the lamp. That again, since this is the 3 synchronization method, there's three lamps. But I think the pictorial is kind of easier to follow. You can see like where exactly all these wires are going. And then the other important thing I wanted to touch on for this, when you read through this, you'll see a couple times it says CCW. This just stands for counterclockwise. So if you ever see that, that's what that means. So it's having you like turn, the dials counterclockwise to 0%. That's again what that means. Just you'd be turning a dial. Of course, you don't do that online. So, and then the other important thing to mention is since it doesn't really apply for you all, since you're not physically doing these skills, but the safety component is really important to read and kind of understand why they're asking those. So that's the first thing that you technically do. If we did this in person, you'd do a personal safety and equipment checklist, and then an electric motor safety checklist. So this is what you do, anytime you're working on a factory on this stuff. It's pretty straightforward in terms of the personal side, like PPE that you should be wearing, all of this. I'm not going to go through because it's pretty straightforward. Equipment safety checklist is pretty straightforward as well. So, remove all obstructions, check for signs of damage, make sure there's no teach pendants from the work area. The electric motor safety checklist is referring to the actual like workstation that you're working on. A couple of the ones that are very important is that the E stop push button is engaged. So what that means is essentially while you're working and wiring everything as according to this, the E stop push button should always be pressed because that means it's off, right? So you can see the E stop push button right here. So that's one of the first things you check is make sure that that is pushed in or engaged because that means it is off. And so essentially if we were to do this in person, you would turn this off, follow the safety checklist, make sure everything was safe, wire everything, call me or whoever your instructor was over, they'd check all the wires, make sure everything looks good. We'd unpress that button, like press it, I guess not unpress, you press it in and it would pop up. And then, we'd run it all and see if everything worked right. So yeah, that's just, a couple things. I'd skim through this. If you look on YouTube, you can see a couple videos that kind of show like the lights in action and exactly what they look like. But essentially all it is like once everything's wired correctly, assuming your alternators were synchronized properly, the 3 lights would blink at the same intensity at the same exact time. But yeah, so I would definitely take a look at this one because it's an important one. It's only 25 slides, and that skill it'll open it up as soon as you click on that. That's the only skill for this one. But any questions about that amateur module or the amateur modules in general? I know we don't normally touch on them, so I just wanted to. Okay, not hearing anything, but yeah, like I said, if there's any other questions or concerns as you go through it, let me know. I know it's hard to be online, but it is nice to have those skills. I'd say that those are the most important thing to take away, specifically for the motor ones and the alternator ones, and then the transformer one I'd say is also important. So those ones in particular, I would really focus on the skills just because I think they're the most applicable to, your future jobs and what you should kind of take away. Okay, so I'm gonna pull up my slides here for week 3. Again, week 3 is on capacitive circuits. It kind of goes hand in hand with next week as well. And let me know if you can't see my slides, because I think it was this class last time, like halfway through, I realized no one could see my slides and I was just talking to a blank screen. Okay, so a couple terminologies from past classes that we're all straightforward on and everyone knows, but just to remind you, resistance and what it is. So resistance is just a measure of opposition to current flow in an electrical circuit. What that means, in simple terms, is current and resistance act against each other. So resistance is a force that kind of slows down current. So that's why we add resistors in circuit. It's a way to slow down the current, and it makes sense because we know resistance means to resist something, right? You're opposing it. It also makes sense if we think about Ohm's law. So if you remember, Ohm's law is V equals I times R. That's how I always remember it. I always then have to like rewrite it. So V equals I times R. If we were to solve this for I, it'd be I again, which is current, equals V divided by R, right? So looking at this equation, this is a reminder that current and resistance work inversely to each other, which means when one goes up, the other goes down. We know that because resistance is in the denominator. So the greater the resistance is, the smaller the current will be. So that is kind of the math behind. So if you ever forget that they're inversely related or that resistance is a opposition to current flow, you can just remember it by thinking of the equation here. Because for example, if we had a voltage of 10 and a resistance of 10, our current would be 1, right? But if we increase our resistance to, let's say, 20, our resistance increased twice as much, and our current decreased by twice as much. So again, just a reminder that these two terms are inversely related. And it's also interesting to note that current is directly related to voltage, which makes sense, right? Because the greater push we have, the faster our electrons are going to go. And we know that because voltage is at the top. So right here we had 10 and 10, but let's say we made the voltage 50, but kept the resistance at 10, then all of a sudden our current would be 5, right? So current and voltage are directly related. An increase in one is an increase in the other, and it makes sense when we think about the definition of both. Resistance and current are inversely related. A decrease in one is an increase in the other. Okay, so resistance, it's kind of that force to maintain a specific flow. It allows us to manipulate circuits and, kind of dictate what the flow is going to be of the current. And we can add resistors in order to restrict that flow of electricity. So this is important because it protects components in the circuit, because we know that too much current or overload can cause harm. So it's definitely a good control measure. Of course, we don't want too much resistance. That can also cause harm. It's always a balancing act, but in general, resistors are very important to kind of manage and control your circuit. So these are the new terms that kind of come up this week, and it is capacitance and capacitive reactance. So capacitance and capacitive reactance, even though they both have the same suffix at the beginning or prefix, right? The capacitive part, they're not the same thing. So for one, they're both measured in different units. So capacitive reactance is measured in ohms. So similar to resistance, which is measured in ohms, reactance kind of does the same thing as resistance, and we'll talk about that in a minute. Capacitance itself is measured in something called farads, F-A-R-A-D-S. So that's a new kind of acronym. So when I say measured, that's just the units behind it. So you could say the capacitance was 50 farads, right? Just like you'd say 10 inches. For the inches is a unit of measurement. For distance, farads is a unit of measurement of capacitance. So again, capacitor reactance, which is again that second term, is similar to resistance. And the way it's similar to resistance is because it resists the flow of AC current through a capacitor. So if you remember last week, we talked about how a capacitor, it's that like, and I can pull up a picture if you don't remember, if you want me to show you. I think I showed that video, and maybe the video didn't work, but essentially it's like these two plates. They're called dielectric plates, and in the middle is kind of this like free-flowing material. And essentially, capacitors are in circuits because they're a way to kind of store energy. And we talked last week about kind of how they work, right? They kind of hold the electrons, the positive and negative charges on both sides of the plate, and it forces the electrons all to accumulate at the bottom of the plate. They're not allowed to flow through the middle, and so all those electrons are kind of stored at the bottom of the plate. So Capacitor, so again, that's what a capacitor is. So capacitor reactance essentially resists that flow of current through a capacitor. So capacitance in itself is the ability of a circuit to collect and store energy, which makes sense, right? Because if a capacitor is the device that stores energy, capacitance is how well it can store energy, right? Because obviously there's certain degrees of that. So the way these terms are related is if you have more capacitance, that means you're storing more energy, right? Because capacitance is the ability to store energy. So if you have a lot of capacitance, you can store a lot of energy. This means that you're going to have less capacitive reactance, because again, that's the term, or reactance is what works against capacitance. So if you have the ability to store a lot of energy, it means that you're not resisting that either. So they work, again, inversely similar. You can kind of think of capacitance and capacitive reactance as current and resistance. They go hand in hand. And so the way that this would be worded in terms of like the terminology is, let's say you have 10 farads, that has less capacitive reactance than 5 farads, because 10 farads means that's our capacitance. Our capacitance of the circuit is 10 farads. That's going to have less capacitive reactance than 5 farads, because it means that you're resisting more on the 5. I just have a quote at the bottom here. So the resistance is the obstacle in the flow of current in an electrical circuit due to a resistor. So let's kind of break that down, right? Because that makes sense. The resistance is what slows down our current in a circuit, and that's because we add resistors, while reactance is the opposition to the charging current due to either an inductor or a capacitor. So next week, the reason I put this in here is because this kind of sets the stage for next week. So reactance is something that is important when we talk about capacitive circuits and inductive circuits, because reactance is in both. So next week, we'll talk about inductive reactance. But this week, it's capacitive reactance because we're talking about capacitance and we're talking about circuits with capacitors. Okay, so there are a couple simple math problems that we can use when we're trying to calculate capacitive reactance. For one, we can calculate capacitive reactance if we're given the frequency and how much capacitance we have, or the capacitor value, which again is measured in farads. So the equation is XC. This XC you're going to see a lot in the upcoming weeks. So I would maybe jot that down, the XC. Whenever you see that, that's just the acronym for capacitive reactance. So capacitive reactance equals 1 divided by 6.28 times C times F, where C is the capacitance and F is the frequency. So don't get that confused with F being farads. F here is just standing for frequency. C is the capacitance. The 6.28, if you're wondering where that came from, that's just a constant, just like how in some equations, like you have, like gravity 9.81 as a constant. It's just, a constant value that anytime you do this problem, it's always going to be that number. So let's say your frequency was 5 Hertz. If you remember, that's the unit for frequency. When we've been talking about waves and all of that, that's how frequent those waves are happening. Capacitor value in this example is 10. So that you would do this problem is 1 divided by 6.28 times your capacitance, which is 10, times your frequency, which is 5. I need my phone for this. So I always do the bottom first, just because sometimes if you do 1 divided by, it'll mess it up. So I would do 6.28 times 10 times 5, and that's 314. 1 divided by 314 is 0.00318, which you can see is what I have written there. And the units for this, that's a horrible 8. That looks like an A, but the units for this would be ohms, which I'm going to draw as this little horseshoe, because again, reactance has the same unit. And we can see, let's say we kept everything the same, except So let's change our capacitance. We're going to increase it to 20. If you do the math here, 6.28 times 20 times 5, that's 628. 1 divided by 628 is 0.016. Sorry, horrible handwriting, I know. So basically, this just shows you again the relationship between capacitive reactants and capacitors, right? When all I did was I increased the capacitor from 10 to 20, and that caused a significant decrease in the reactance, which is the resistance here. Any questions about this math? So I think there are a couple questions that will ask you to solve for capacitive reactance. Again, you're going to use this equation, assuming you're given frequency and the capacitor or capacitance. So I would write down this equation if you don't have it already. And again, that 6.28 is a constant value. Okay. Gone a little too far ahead. So just a recap on topics from ELT 120. So if you remember in ELT 120, we learned that for series resistors, we could calculate resistance by just summing up all of the resistor values. So as a reminder, R1 plus R2 plus R3, let's say there were 3 resistors, 3, 10, and 5. We just add all of those together. The sum is the total resistance. For parallel, we use this equation, which in this we could only use if we had 2 resistors. If we had more than 2, it's that more complicated equation. Multiply the 2 resistors by each other and then divide it by the sum. So this does come back into play for ELT 126, and that is because when we're dealing with reactants and resistance in a circuit, which you can't deal with both terms because you might have resistors and capacitors, you can essentially combine these together to find the total resistance in the circuit because they have the same units. Anytime something has the same units, you're able to add it together. And you know that reactance is in ohms and resistance. So the way that this would be worded is, let's say we have a series circuit with an RMS voltage. As a reminder, RMS stands for root mean square voltage. So essentially the average voltage of 20 volts AC. And you have 2 capacitors with reactances of 4 ohms and 1 ohms. What will be the total current in this circuit? So you can treat that reactance as resistance essentially and add it together. So 4 plus 1 ohms is 5 ohms. So that essentially is your total resistance of the circuit. So you can treat that as RT or total resistance, and you can easily find the current by using Ohm's law, which is V equals I times R. So V divided by R. So 20 volts, because it told us that that's the average voltage, divided by 5, which was the resistance that we found, to give you 4 amps. So essentially, it's the same math that you had to use when in ELT 120 when we were doing problems with Ohm's law. But this time, instead of having resistance, you're having reactance. But it's essentially the same math because reactance is just another form kind of resistance. So any questions on doing a math problem like this? Hopefully this one was pretty straightforward as well. Alrighty. So the other thing I wanted to talk about, and again, please slow me down if I'm going too fast. The other thing I wanted to talk about was graphing voltage and current. So we've talked a lot about in this class how when you graph voltage and current over time, they create a sine wave, which again, a sine wave is just like a mathematical wave that has a specific like frequency and wavelength and all of that. For voltage and current, when we graph them over time, when we graph the frequencies over time, you can see that the current wave has a 90-degree phase shift ahead of the voltage sine wave. So what that means is if we were to graph them, the current here, you can see it starts lower, right, than the voltage. but as we graph it over time, the current is a little bit ahead of, you can see right here, the red line is a little bit ahead of the blue line, which is the voltage. So, and it's ahead by 90 degrees, essentially. And if you're wondering, like, what do you mean by 90 degrees? That goes back to that unit circuit, and how, if you remember, like, when we had that unit circle, each segment of the unit circle was a different degree. You had like pi, 2 pi over, then you had pi, 3 pi over 2, 0.5 pi. You had all of those numbers. All of those numbers were assigned a certain degree. And that degree essentially kind of serves as distance. So all you really have to know for this class is that when using a capacitor, your current wave is kind of ahead of voltage, if you were to graph them. Okay, so the last little bit of this week is talking about impedance. So impedance is another term. And essentially what impedance is it's the sum of reactance and resistance. So I might have misspoke a minute ago when I said, like, oh, you can just add the resistance and reactance together. You can, but it's a little bit more complicated, which we'll do a problem in a minute here. This problem is a little bit different because we weren't given resistance. We were only given the reactances, right, of 4 ohms and 1 ohm. So there was no resistance. So we could simply just add it together and treat that as a resistance. Sometimes you'll have reactance and resistance together, and impedance is kind of the term that combines both of those. So I just kind of wanted to walk through, and this is the last slide I have, so we'll spend some time on it, but I wanted to walk through this that was done in the video to kind of break it down and talk about it a little bit more because it's important. I know sometimes as you're during the videos, since you don't like have the ability to stop and ask questions, it can be kind of hard. So which is why I wanted to go through this. So impedance is something that you will need to calculate a lot of times. And essentially for the next 2 weeks, we calculate it because impedance, once we have that value, it kind of allows us to find other values in the circuit. It kind of works a lot like 120, how like it was solving a puzzle, right? Like once we found what the current was, then we could find what the voltage was, then we could find what the voltage drop was, right? Like you could find slowly, you could solve the circuit by finding one component at a time. And that's why impedance is important. Impedance itself isn't that valuable to know, but it's the terms such as, current and voltage drop that are important to know, and we need impedance in order to calculate those. So I have these written down on the side. I would write these down because it can be hard to kind of follow everything and what the units are for everything. So we know that V stands for voltage. We talked about how X, and it's a little c, but sometimes it's just denoted as X. You can see the XC is right here. That's capacitive reactance, right? We talked about that earlier. R is resistance, we know that. I is current. Z is the letter that is used for impedance. So when you have the equations here, Z is used for impedance. So you can see these two equations up here. VT equals VC plus VR squared. ZT equals XC plus R squared. So those look a little bit confusing, but they're really not. Essentially, they're just Pythagorean's theorem. So I think I'm assuming that's the math you've been doing with Kim. But you probably know Pythagorean's theorem as a squared plus b squared equals c squared. But when you have to solve for like c, right? Because like that's finding the distance of one triangle. You know how you use the equation c equals square root of a squared plus b squared. And if you're wondering, because I actually think it's important to know for this, I don't know if Kim went over this, but has she gone over Pythagorean's theorem with you guys?
Yeah, we covered that in the first week.
Okay, perfect. So I'll just skim this then, but thanks. I just wanted to make sure before I confused you. But Pythagorean's theorem is a squared. Oh, I have it written here. A squared plus b squared equals c squared. But if you just want to solve for like one leg of the triangle, if you have a triangle like this, where you have a squared, B squared, or A not squared. But you have, sorry, okay. So you have a triangle, has three sides, A, B, and C. And let's say you know the length of A and B, you can find C by using the equation C equals the square root of A squared plus B squared. And all this equation is the equation above it, just isolated for C. So this equation here and this equation here are the same equation. It's just instead of being C squared, it's C. So all we did was to get rid of a square root, or to get rid of a square, all you have to do is square root the other side. So that's important to note. So square, I don't know if Kim talked about that, but a square root is just the opposite of something being squared, which makes sense, right? Because like something squared is multiplying it by itself, right? Like 5 squared is 5 times 5. It's multiplying the number by itself. The square root, like the square root of 25 is, this essentially means what two numbers multiplied by itself equal 25, and it's 5, right? 5 times 5 is 25. So they're opposite of each other. The square root of 25 is 5. The square roots, all it's doing is essentially finding the number that is multiplied by itself to get that number. So they're opposite of each other. So that's where the square root comes from, if you're wondering. It's just the opposite of something being squared. The reason we're talking about it for this class is it goes back to this idea. Impedance is like, essentially, if we were to draw out reactance and resistance, impedance is the C part of the triangle, right? So if this reactance, let's say reactance, the length of it is A, resistance is B, impedance is C. That's the length of a triangle. The reason they draw it like this is to show you or to remind you of the equations. So essentially what it means is A squared plus B squared, or reactance squared plus resistance squared, equals impedance. And that's what this equation is. So impedance is just the reactance squared plus, or the square root of reactance squared plus resistance squared will give you impedance. And again, impedance is important to know because once we have impedance, we can solve for other parts of the circuit. So for this problem, they gave you that the capacitive reactance and resistance were 3 and 4. Again, they're both in ohms because we know reactance is in ohms and resistance is in ohms. So we can kind of combine them together. So I would first, that's why in the videos, Eddie draws out the triangle here and he puts a 3 on one leg and a 4 on the other leg. That's because one's the resistance and one is the reactance. I can't remember which is which in the video, but it's irrelevant because you're doing the same thing with it. We don't know what the impedance is, but we can easily solve for it, right? Using Pythagorean's theorem or using this equation up here. We just do the square root of the capacitance squared plus the reactance squared. So in this problem here, it would be Z, which is impedance, equals the square root of XC squared plus R squared. So that's 3 squared, which is 9, right? 3 squared, 3 times 3 is 9. Plus R squared, which is 4. 4 squared is 16. So Z equals the square root of 25. 9 plus 16. So Z equals 5. So what that tells you is that the impedance equals 5 ohms. And again, we're dealing with ohms here because we're dealing with resistance and reactance, which are measured in ohms, so is impedance. So that's the first part of this problem that they do in the video, is just solving for impedance. So again, the way that we solve for impedance is you take the reactance and resistance, which are going to be given in the problem, square them, add them together, take the square root, just use Pythagorean's theorem. So now once you have impedance, impedance can kind of serve as your total resistance in a circuit that has resistance and reactance because of the fact that it's a combination of both, and we know that both forces work similar. So we can solve for current or voltage if we have impedance, because impedance is kind of the way that we combine resistance and reactance. So here you can see what they're doing in this step 2 is they're solving for current. So in the video, and if you haven't watched it yet, it's okay because we're talking about it right now, but in the video, you're given that the voltage is 12 volts of the circuit. And again, this is of the circuit. So essentially you have a circuit that has a resistance of 3 ohms, a reactance of 4 ohms, and a voltage of 20 volts. We know that the impedance is 5. So essentially we can solve for current by using Ohm's law, which is I equals V divided by R, but instead of R, it's Z because of the fact that Z is just a combination of both of those terms. And if we just did R and just use the resistance, that would be wrong because we also have to account for reactance. So we can solve for current by simply just doing 20 divided by 5. And again, that 5 comes from Pythagorean's theorem and the impedance there. So that gave us the current of 4 amps. So if you were to draw the circuit, this is what it would look like. So we know this is an AC circuit, so that's why you can see that this isn't a battery. It's shown by the like circle with the sideways S. That's the symbol for AC, kind of, which the reason for that, it's not sideways S, it's showing like the sine wave or the fluctuation of current. We know we had 20 volts because it gave us that. We had a resistance of 3 ohms, that's what this is, and then we had a capacitor of 4 ohms. So capacitors are denoted by this symbol, which kind of looks like a battery. This right here is not the battery. This is showing capacitor, which makes sense that it's those 2 lines because it's like indicating or symbolizing the 2 plates. So the third thing we would do for this problem is once you solve for impedance and solve for total current, you could now solve for the voltage drops. And the way you would do that is I times X and I times R, where X is your reactance and R is resistance. So essentially there's 2 voltage drops in this location. There's a voltage drop with 3 ohm and a voltage drop with a 4 ohm resistor or capacitor. So you would use I, which is the total current, which we know is 4. So 4 times 3 and 4 times 4, so 16 volts and 12 volts. Those are the 2 voltage drops. The voltage drop at the 4 ohm capacitor is 16. The voltage drop at the 3 ohm resistor is 12. And that's essentially the math you would have to do. So again, all we did for this problem is it was just using Pythagorean's theorem or this equation up here to solve for impedance. That was step 1. Once we had impedance, we could solve for total current. Once we had total current, we could then solve right here for the voltage drops. And you'll notice next week, it's almost identical, the math we do. When we talk about inductive reactance, essentially it means we have an inductor in a circuit and it works similar to resistance, and the math is pretty similar as well. But yeah, so basically there's a couple quiz questions that I think will have you, they'll probably be, I remember correctly, it's like it'll talk about a circuit, and one problem will have you solve for impedance. The next problem on the quiz will like ask you what the current was, and then you might have another question or two on what the voltage drops were. So that's a pretty big chunk of the quizzes for this week and the concepts that are important to know. But with that, we have 15 minutes, so a little less than 15, but basically that was all of the important concepts I wanted to talk about. Some main things are just understanding kind of what capacitive reactance is, what capacitance is, doing the equations where you have to calculate capacitive reactance given, frequency and capacitance, and then using math with impedance. So being able to use Pythagorean's theorem to solve for impedance, solve for total current, and solve for the voltage drop. So they're kind of the main components of this week. But with that, I've been talking for a while now, so I'm going to pause, see if there's any questions, anything you want me to go back on. Hopefully this was helpful. Yeah, this is all I had for you. So I'll hand it over to all of you if there's questions.